Okay, today we will be talking about the coordinate transformation. So let's first talk about why do we need it, what is it, and then we will do the formulation. Now if you go back to our previous example problem, where we have a beam member and a truss member, and when we do the discretization, let me just draw the discrete version of it. So I have a member here, another member here, this is the node B, and we have this truss member. And when we write down the degrees of freedoms, now this is the element axis, it goes from start node to end node. So we said that that's D1, D2, D3 and D4. And when we look at the truss member, we said that that's the direction, meaning that this point is the start node, this point is the end node, and the axial forces are defined along the element axis in these directions. So let's show it this way, in this direction. Okay, and then we said that that's D1 for the truss member, that's D2. Now when we look at the directions of these forces, the directions of the forces defined for the first member, for this beam member, and the directions of the truss member, they actually do not lie in the same plane. I cannot directly add D2 with D3 or so on. I have to divide this D2 into its components. And the way we were doing it, we were dividing it, the component would be as follows. We were actually defining a coordinate system, global X and Y, and we were dividing the forces or the displacements of this second degrees of freedom by using the coordinate system that we defined for this for the whole structure. I mean, we were doing it, we were not showing it. Okay. What was the advantage if I say that if I have here d2y and d2x, okay, when I divide this forces or the displacement into its components, what was I doing? When I was writing the stiffness coefficients, or while determining the stiffness matrix, I can draw the free body diagram as follows. So let's again draw it one more time. Let's say that that's the truss member, and we have, let's assume that I have K33 here and K43 here. If I have the forces at the end of the truss member defined in the global X and Y axis, I would have the following forces. Let's call the truss member or K2X. These are the components. K2Y. Now as you see, all the forces, all the end forces or all the stiffness coefficients are now defined in the global X and Y directions or in the same coordinate system. So the advantage of it, so when we want to calculate the global or the structural stiffness coefficients, let's say that K11 and I got K21 here, I don't have to worry about the directions of the forces, how they are defined, to which axis, since I know that all the forces are defined with respect to the global coordinate system, with respect to this X and Y. I can directly say that K11 will be equal to K33 coming from the first member plus K2Y coming from the second or the truss member. Now if I know all the stiffness coefficients are defined in the same coordinate axis, I don't have to worry about drawing any free body diagram. All I need to do is to add directly at the coefficients coming from each member. Of course, drawing the free body diagram for us is not a big deal, but it's a big deal for a computer. Okay, so we have to find a simpler way of implementing this formation of the stiffness matrix. So one way of doing that, defining all the degrees of freedoms in the same coordinate system. If we do that, the formation of the structural stiffness matrix is very straightforward. You just add coefficients coming from each member. Now, the question is, how can I convert the coefficient defined in the elements axis to another coordinate axis? That's the question that we are asking to ourselves. Remember that if you go back to our previous example, we were always using the geometry, right? We were trying to figure out, we were drawing triangles, trying to figure out the angles of inside these triangles, and by using some trigonometric relationships, we were calculating first what these coefficients are. Now, what we are going to do here today is we will try to formulate that. We will try to formulate what we were doing, what we did previously. Okay, so we will have some formulas for it, and then we will apply those formulas to convert the stiffness coefficients defined along the element axis to another axis. So we will have some formulas for that. So in order to do that, let's draw some figures. Let's draw a 2D plane. So we will be doing this formulation for 2D. So I have a 2D plane. Now let's draw the coordinate axis. So let's say that the black line is the axis defined in global coordinate system. So this is our global or the structural coordinate system. And let's draw another coordinate system. So let's say that that's x prime, that's y prime, and z prime is parallel to z. So we have two coordinate systems. One of them is x, y, z. So we will call them global or structural coordinate system. So we want to convert all the forces, all the displacements into a global or structural coordinate system. We also have x prime, y prime, z prime. We will call it local or member coordinate system. Okay, so the member coordinate system for us actually defines the coordinate system that belongs to these members. Okay, and we want to relate the member coordinate system with the global coordinate system. So what is that relationship? How do we define it? So we will define a rotation angle. We start from the global x, and we draw it in the counterclockwise direction, and we go to the local x prime. So this angle is theta, and we call this angle as the rotation angle. Okay, so how do we define it? Again, let's repeat. Start from the global x, go in the counterclockwise direction, and find out the angle between the global x and the local x prime. That's our rotation angle. And now let's say that I have two vectors. This is F1 in the global x direction, and then I have another vector F2. Let's also show the third vector, it's in the z direction, F3. Now I want to calculate the components of F1 and F2 in the x prime and y prime axis. Okay, so in order to do that, again I will be drawing triangles. So I am drawing a triangle like that. So F1 has this component on x prime axis, and F2, let's draw another triangle here, and if you think about it, this angle is theta this time, and this is the component of F2 on x prime axis. So if I say F1 prime is equal to the component of F1, so F1 times cosine theta, and the component of F2 plus F2 times sine theta. Oops, let me erase this part. So the component is, we'll have an F1 prime like that. Okay, so what about the component on the y prime axis? So let's extend this y prime axis like that. Now the component of F1 on the y prime axis is this one, it's in the opposite direction, and the component of F2 on y prime axis is this one. Now let's write F2 prime is equal to minus F1 times sine theta plus F2 times cosine theta. Okay, and F3 prime will be then equal to F2. We don't have any rotation. If I write this thing in matrix form, we will have the following relationship: F1 prime, F2 prime, and F3 prime is equal to cosine of the rotation angle, sine of the rotation angle, minus sine theta, cosine theta, 0, 0, and I got zeros here, and 1. I got F1, F2, F3. Okay, so we call this matrix as our transformation or rotation matrix. And it's shown by, usually shown by lowercase r. So in matrix form, I got F prime is equal to rotation matrix multiplied by F. Okay, so this shows when I have a vector components. You can think of these vector components are, I got three displacements, okay, defined in the global directions, and I want to find their components in the local coordinate system. How can I do that? If I multiply these displacements, or you can just think of it as membrane forces, okay, in the global directions with the rotation matrix, I can directly obtain the components defined in the local coordinate system. Now the question is, okay, we did it for a single node, but how can I transform the end forces or the end displacements of a structural member? Okay, so let's see that. Let me erase that part and write it in here. So how can I transform the end forces or the end displacements for a structural member? Now let's draw a typical frame that we use in most of our examples. So I have this frame, and let's put an inclined member, because when the members are orthogonal, we can also find ways to assemble the stiffness matrix without the rotation matrix. But when we have an inclined member, then this is a problem. So now I have a global coordinate system. I'll just say CS for the coordinate system, and I want to, this is the inclined member. Okay, so for that inclined member, let's draw it here. And remember, the way we define the degrees of freedoms are as follows. We say that that's the start node, let's call it I. That's the end node, J. Remember our derivation of the element stiffness matrix, that's the way we started. So that's the start node, end node. It goes from I to J. And then now we will define a local coordinate system. So this is x prime for this member, and this is the y prime. Remember that we use this kind of coordinate axis deformation when we try to analyze the structures by using the double integration. It's the same thing. So let's again put some definitions. Now when I define it this way, I will become a start node, and J for me is an end node. And this x prime, y prime is a local or member coordinate system. Now let's define the rotation angle now. Remember that this is our global x. So from the global x, I will go in the counterclockwise direction from global to local x. That will give me the rotation angle. So I related the coordinate axis, the global coordinate system of the whole structure, with the local coordinate system with the rotation angle. Now let's show member forces. Let's isolate that member. So member forces in local coordinate system. So let's draw the member one more time. That's our member. With the arrow we are actually showing which one is the local start node, which one is the end node. So this is a local system. So here I have an axial force, let's call it F1 prime, a shear force F2 prime, and a moment, that's F3 prime. At the end node, axial force F4 prime, shear force F5 prime, and rotation F6 prime. So all these member end forces are defined along the member's local axis. Now let's show the same thing in the global coordinate system. Now this time everything will be defined according to the global coordinate system. Okay, so I no longer say that this is an axial force or a shear force. So I have F1 is the force defined in global X. F2 is the force defined in global Y. Rotation is the force actually defined in the global Z. So I have F4, F5 and F6 here. And this is the forces defined in the global coordinate system. Now, what I want to do is to relate the forces at the start node defined in the global system with the forces at the local system defined in the local system. Okay, so let's do that, and in order to do that I will be using this equation, this relationship. Now I will write my equations as follows. F in the local system is equal to rotation matrix multiplied with the forces in the global system. Now I actually have written this equation in a different form. Now in that equation R will be equal to small r, that rotates the forces at the start node, no coupling, and small r, that rotates the forces at the end node, and this will be a 6 by 6 matrix. So this expression, this equation actually converts the forces, the end forces of a member defined in the global system to the end forces defined in the local system. And that's the relationship. Let me erase this part now. I will keep the figure. Let's erase that. Now we can actually, since the end displacements are vector quantities, we can just write the same thing for displacements. So for member end displacements, we can write a similar equation. I can say that the displacements, member end displacements defined in the member's local coordinate system is equal to the rotation matrix multiplied by the displacements defined in the global coordinate system. So this is our second equation, and if you think about it, that's a global to local transformation. So with these equations I was able to transform member end forces and member end displacements defined in the global coordinate system into the local coordinate system. Now I should find a way to do the reverse. When I have forces defined in the local system, how can I convert them into the forces defined in the global system? So let's try to figure that out. Now for this I want to examine the properties of this rotation matrix. So when you look at that matrix, this one, we will see that it's a unit orthonormal matrix. So what does it mean, unit orthonormal matrix? Let's write what it is. So R is a unit orthonormal matrix So unit matrix, we know that if you take the determinant of this matrix, it's equal to unity. Now orthonormal means R inverse, the inverse of that matrix, is actually equal to the transpose of it. So that's a very nice property for us, because I don't have to invert any matrix, this type of matrix, and I can, since it's a unit matrix, I can write the following relationship. R transpose multiply with R is equal to the unity, identity matrix. Okay, now that's a very nice property for us. We will see why, but before that, let me erase this part. Now, let's take the displacement transformation equation. So we have the following equation again. U prime is equal to R rotation matrix multiplied by the displacements defined in global. If I pre-multiply both sides with R transpose, so pre-multiplying both sides with, sorry for that, what do I get? The following relationship. R transpose multiplied by U prime is equal to R transpose multiplied by R and multiplied by U again. And we know that this is R transpose times R is equal to the identity matrix. So if I rewrite that equation, I end up with the following. U, or the displacements defined in the global coordinate system, is equal to R transpose multiplied by the displacements defined in the local coordinate system. So as you see, this equation transforms the forces in the local coordinate system into forces or displacements in the global coordinate system. So basically this equation is local to global transformation. And I can write the same equation for the forces. So forces in the global coordinate system is equal to rotation matrix multiplied by the forces defined in the local coordinate system. So this is the equation for the forces. Okay, now we see how we can transform forces and member end displacements from global coordinate system to local coordinate system, or vice versa. Now the question is, how can I transform the stiffness coefficients? That's what we want to do actually. So let's see that. Okay, and for this again, let me erase this part. And we will do the calculations in here. Let's also erase all these things. Again, I will draw the figures and then do the derivation. Now this is our member, right? That's the start node, that's the end node. Now let's show the stiffness coefficients. If you think about our derivations, I got K11, K21, K31, right? I'm doing it for just a single row. K41, K51, and K61. Here you see 6 by 6 matrix. So I actually combined the truss stiffness matrix with the beam stiffness matrix. So this is a frame stiffness matrix, and this is just the first case. Now we want to convert it into this force. I got K11 defined in global X, K21 defined in global Y, K31, 41, six, 1. So how do we do that conversion? We did it for the forces. Let me put the local signs here. We did it for the forces. We did it for the displacements. How can I do it for the stiffness coefficients? Okay, so let's start from here. Now we know that the member and forces defined in the local coordinate system is equal to element stiffness matrix. We derive it for the local coordinate system multiplied by the member and displacements defined in the local coordinate system. So this one is the stiffness matrix, the element stiffness matrix that we derived in local coordinate system. If you think about our derivations again, we were deriving the stiffness coefficients by using the member's local axis. Okay. Now, we know that the F prime is equal to rotation matrix multiplied by F. We derive that relationship. Okay. And that's equal to K prime, and instead of writing U prime, I will be writing R prime times U multiplied by R times U. So instead of U, I will use this relationship. Okay. Now, if I pre-multiply both sides by R transpose, what do I get? I have R transpose times R times F is equal to R transpose multiplied by K prime multiplied by R multiplied by U. Now we know that this is identity, and at the end of the day we end up with the following relationship. And forces defined in global coordinate system is equal to R transpose times K prime times R multiplied by the displacements defined in global coordinate system. And if you think about it, the results of this matrix will relate the displacements in global coordinate system with the forces in global coordinate system. So we define this matrix as our K, and it's the stiffness matrix or the element stiffness matrix. Let me rewrite it one more time. In global coordinate system, So what we are trying to say here is, if you multiply the element stiffness matrix that we derived before with R transpose and R, you obtain the stiffness coefficients defined in the global directions. Now, if we have the stiffness coefficients defined in the global directions, then we can directly add them to obtain the structural stiffness matrix. So in our next class, this is what we are going to do. Now I will be formulating the element stiffness matrix in global coordinates. Now let's start from the truss member. We did that, we drew the element stiffness matrix before, but I will do it in a little bit different way. I will define some additional degrees of freedoms for that. Now let's again take a truss member. So this is node I, this is node J. Now I will do the derivation in the local coordinates first, and then transform that into global coordinates. So if you think about it, this is the x prime axis, that's the way we define start to end, and that's the x prime axis, and this will be the y prime axis. Now the degrees of freedoms, this is the first degrees of freedom, d1. I will also define the second degrees of freedom like that, d2, d3, and d4. Now I can directly write what the stiffness matrix is. We already derived that before. So I have EA over L here. So when I want to give a unit translation in the first direction, the force is EA over L. Of course, I don't see any force in the D2 direction. This is 0. In the D3 direction, that's equal to -1 and 0. Now the stiffness, the truss cannot give any resistance in the D2 direction, right? Because by definition this end is free to rotate, this end is free to rotate. If I want to move it in the upward direction, I don't get any resistance, so it's all 0 here. And likewise I have -1, 0, 1, 0, and 0, 0, 0, 0. So that's the stiffness matrix of the truss member. Of course, if you look at that stiffness matrix, is nothing different than our previous derivation. The only difference is I added these 2 degrees of freedoms, D2 and D4, in my definition, and I put 0 because by definition truss doesn't have any shear resistance, and I didn't show any rotation degrees of freedom here because we are not going to use it. Now let's give some inclination to the truss member, right? So this will be the x prime axis, that will be the y prime axis. So the rotation angle, if I just say that that's the global x, that's global y. By definition, we go from local x to global x to local x prime in the counterclockwise direction. That's the rotation angle. And the degrees of freedoms defined in the global directions are as follows. That's d1, d2, d3, and d4. But before moving forward, let's put some primes here so that just to show that these are all defined in the local directions. Now the element stiffness matrix defined with respect to these degrees of freedom defined in the global coordinate system is defined as follows. Remember our previous derivation. I say that K is equal to R transpose multiplied by K prime multiplied by R. That's the equation that we derived before. So we just write it in the matrix form. I got cosine minus sine and sine, that's the R transpose, 0 0 here, and again cosine minus sine and cosine multiplied by EA over L times the stiffness matrix, that's minus 1 0 nothing here, minus 1 0 1 0 and nothing here, multiplied by the rotation matrix itself, that's CS minus SC 0 0, and likewise CS minus SC 0 0 0 0 here. So when you perform this calculation at the end of the day, this is what we get: EA over L cosine squared cosine sine minus cosine square minus CS S squared minus CS minus S squared cosine squared CS and S squared. That's a symmetrical matrix. Okay, now if you remember, if we go back to our truss example, let me draw it right here. This example, we worked on this, right? So let's take a look at this member now. Right, according to our definition, if this is define it this way, that will be my rotation angle. And if we want to give a unit translation, let's just draw the stiffness matrix for this direction, for D1. So how much force do I need to move this truss in the upward direction? That would be K44, right? So this is K44. So what is K44 equal to? We go to this matrix, it is S square multiplied by EA over L. I think we already derived that coefficient in our previous solution, times sine square theta. Okay, what is this coefficient? K34, what is that? So I go to this again matrix, K34 is this one, and that's equal to EA over L multiplied by cosine theta times sine theta. So as you see, without going into too much trouble, without giving a unit translation in the upward direction, without finding its component in the elements axis, we directly obtain it, these coefficients, from the global stiffness matrix. Now, in this sheet, you see all these matrices. We have the element stiffness matrix in the local coordinates. This is the rotation matrix. And when you do that transformation, R transpose K prime times R, we obtain the stiffness matrix in the global directions. Now I can do the same thing for the frame element. Remember that we already derived the 6x6 frame element stiffness matrix. So all I need to do is to multiply it with R transpose and R, and then I obtain the final stiffness matrix. Now the directions of these stiffness matrix is defined in the global directions. It's shown here. So if I want to move this, give a unit displacement in the global x direction, the force that I need will be this much. And if I want to keep the vertical translation equal to 0 when I have a unit translation in x, the force that I will be needing is this one, and so on. So we can use actually this stiffness matrix directly the way we determine the structural stiffness matrix. There is no difference, only the coefficients are a little bit different. We have the rotation effect in these coefficients, but since the directions of all the members match, you will see that it will become very easy to assemble to obtain the structural stiffness matrix. And in the upcoming example problems, this is what we are going to do.